This is a recording for Edexcel Further Pure 1, Coordinate Systems 1, the Parabola and Rectangular Hyperbola. Section 1.1, Parametric Equations. Before you start this section, it would be advisable for you to be familiar with the following topics from core pure mathematics. Firstly, simple curve sketching, so for example straight lines and quadratic equations giving you parabolas, and then being able to find the coordinates of points of intersections of these. So if we have that, we have maybe two points of intersection which we can find by solving quadratic simultaneous equations. For the videos towards the end of the section, then we also are required to find tangents to curves using the idea that the gradient can be found from the derivative dy by dx. You won't need to be able to differentiate the functions we'll be looking at. However, the idea that we can use the gradient function dy by dx and then the straight line equation to give us the tangent is what's required. Well, this video looks at the idea of parametric equations. You'll already be familiar with Cartesian equations, so for example y is equal to x squared plus 3x is a Cartesian equation. It involves two variables x and y. If we have a parametric equation, there are two separate equations, one for x and one for y, involving a third variable known as the parameter. Often we use t for the parameter, although obviously we can use different letters. So two completely separate equations which then allow us to calculate the x and the y coordinates for different values of t. If we've got three-dimensional graphs or three-dimensional functions, then we'd have a third function for z. Let's look at that idea in a little bit more detail. Here we've got the same parametric equations for x and y, so x is equal to 3t, y is equal to t squared. And you'll see here that there's one point being plotted. It's at the value of x equal to 3 and y equal to 1. So that's when t is equal to 1. Now t can take literally any value. So we could have it when t is equal to 2. We would get x is equal to 3 times 2 is 6, and y is equal to 2 squared, which is 4. So 6, 4 would be the value when t is equal to 2. If t is equal to 0, we'd have x is 0, y is 0. So this particular curve is going to go through the origin. And that's the value we'd get when t is equal to 0. T could be negative. So for example, at negative 1, we would get x is negative 3 and y is negative 1 squared, which is 1. So the point 3 and 1 would be our value here when t is equal to negative 1. And literally any values. Now it looks like it's going to be fitting a curve that you're quite familiar with, but to give you a better idea, I'm going to look at this on a graphics program. So this is the same set of parametric equations, x is equal to 3t and y equal to t squared, and you can see at the moment we've got t is equal to 1, and that we have the point at here 3, 1. If I vary t, then we'll see what happens. There's t going back to 0 and we get to the origin. Negative 1 was the point we had there at negative 3, 1, and so on. So the point moves for different values of t along a curve. And here's the curve that the point follows. Looks very familiar, doesn't it? It looks like a parabola. But how can we actually prove that? Well, we know that what the equation of a parabola would look like if it was a Cartesian equation. So what we want to do is to take our parametric equations and see if we can turn them into a Cartesian equation. And that would involve eliminating the value t from our equations. Well, it's a pair of simultaneous equations, and so from x is equal to 3t, then it's easy to see that t is equal to x over 3, and we could substitute that into the equation for y, so that y is equal to t squared, so that's x over 3 all squared. In other words, it's x squared over 9. And that's a familiar equation. Y equals x squared is a standard parabola. This is just divided by 9, so it's a scale factor, and therefore this is a parabolic equation. So in general, if we've got parameters t giving us two equations, one for x and one for y, then to find the Cartesian equation we need to eliminate the parameter t. So this is the important thing, eliminating t. And we can do that in a variety of different ways, so I'll just show you two for this rather straightforward set: x equals at squared and y equals 2at. Well, one way that we could do it is the way that we've just seen, where we know that if y is equal to 2at, then that tells us that t is equal to y over 2a. And we can substitute that into the equation for x, so that x is equal to a multiplied by y over 2a all squared, which is therefore a multiplied by y squared over 4a squared. And there we get cancelling out of an a. If we then multiply by 4a, we get the equation, or the Cartesian equation, y squared is equal to 4ax. An alternative way would be to recognize the fact that we're going to need t squared, and so we can get that by simply squaring y. So we can see that y squared is equal to 4a squared t squared. But because we know that x is equal to at squared, we could write this as 4a multiplied by at squared, which is x. So we've arranged for our equation to have an expression which is equal to x, and therefore y squared is equal to 4ax. So two different ways of eliminating that parameter t. Now notice that t is the parameter here, not a. You don't need to eliminate a. That is simply part of the expression. It would be a constant within our parametric equations. It's not a variable. There are those two different methods typed out rather neatly for you to look at. But in general then, what you're trying to do is to eliminate the parameter from the pair of equations that you have, to leave us with Cartesian equations, a single Cartesian equation involving x and y. Well, that's the end of the first recording in this section. In the next one, we'll be looking at the idea of conic sections.